So the standard cosmological model is very successful. You can see in a couple of examples how successful the theory of primordial abundances of the light elements will give you predictions which are in very good agreement with what is measured for a number of the light isotopes. The angular power spectrum of the microwave background sky is very well fit by a model coming from the general relativistic theory of the development of cosmological perturbations. And in fact, from that fit, you can derive the abundance of dark matter in the universe. It comes out to be a very important, large number. Now, and so there are actually other successes, but I won't go into them. But the moment that you try to use the elements of the cosmological model to try to understand galaxies formed in the universe, there are some problems which arise, which are well known. And the talk is about how an early perception of these problems led to Mond, what the physical basis of Mond might be, what the successes and failures of Mond are, and how to try to fix those failures, and about the ongoing effort to make Mond into a completely correct relativistic theory. So let's get started with some facts. Rotation curves of these galaxies are flat. This collage was made by using radio Doppler data from CO molecules in the inner parts of these galaxies, H1 lines in the outer parts and optical lines in the middle to construct a rotation curve for a variety of galaxies. You can see that the curves are very flat, way out from the optical radius of the galaxies, and this is a fact that has to be explained by any theory of formation of galaxies or structure of galaxies. The amplitude of these curves is given by the Tully-Fisher law, which there are two versions of it. One is the 1980s version of Aronson and company, which says that the luminosity in the K-band, in the infrared K-band, is proportional to the fourth power of the velocity in the flat part of the rotation curve. As you can see, it's a very good fit for a group of galaxies, these galaxies. And in the modern version, this century's version, Magov's, the baryonic mass in gas and stars in the galaxy is proportional accurately to the fourth power of the flat, velocity in the flat rotation part. The velocity in the flat part of the rotation curve. It's also a very accurately obeyed law. And as you know, the Tully-Fisher law is used to measure distances, extragalactic distances, but it's very important to understand why it works, and I'll have something to tell about this too. The usual way of understanding these two facts is with the dark halo paradigm, which goes back to the idea of Ostraker and Peebles that this galaxy is embedded into in some massive dark halo. Now, if this halo has a mass density going like 1 over r squared, you will get, especially if that happens in the out of the central regions, you will get a flat rotation curve. So that seems to be a good idea. Now, there are more modern cosmological simulations which tell you that the profile of a halo formed naturally in standard cosmology is the red line, the blue line, NFW, compared here in this log-log plot with the profile of an isothermal sphere, the 1 over r squared profile. And you see there is a difference. The standard halos that form will go like 1 over r in the inner regions, and more importantly, will drop like 1 over r cubed in the outer regions. So only the middle region is really giving you a flat rotation curve. If you go too far out, there is no support for the flat rotation curve. So one failure of this cosmologically originating idea is that you cannot really get extended flat rotation curves all the way out. There are other problems, like the need to fine-tune the models. The reason is that if you look at the disk should give you a rotation curve like this because it's rapidly dropping in a mass density exponentially, actually, the halo would give you a flat rotation curve. It's about a 1 over r squared profile. And if you join these two contributions, you might get a feature in the rotation curve, which is usually not seen. So it's necessary to fine-tune the parameters of halo and disk to get rid of this feature. And nobody likes to fine-tune things. The Tolley-Fisher law is also a fine-tuning problem because the luminosity comes from the disk, and the velocity is mostly from the halo, especially in the outer parts. So you have to, again, fine-tune to get this nice, very nice correspondence that you saw in the graphs. And there are other problems. For example, too many satellites in the cosmological simulations, too many small halos formed together with a big halo, which means we should see a lot of little galaxies, satellites to every big galaxies. And at least for the Milky Way and Andromeda, this is not true. This is not true. The subject is, of course, being investigated still, but there are too many satellites. Now, the hope of people that support the dark matter way of understanding galaxies would be that the hydrodynamic flow of baryons into the dark halos should contrive to make should contrive the fine-tuning that we need here. And it also should make sure that some of the satellites, some of the small halos, do not get too many baryons so that they do not become visible, and so you don't have too many visible satellites of big galaxies. We heard a talk, a nice talk in the symposium, mini symposium yesterday, the Mond, by Gary Mammon that showed us how hard it is, hydrodynamically speaking, to try to understand all these facts. It's really not a well-advanced subject yet. I will show you that in Mond it's much easier to understand all these facts. And finally, there is the problem of the COSPI halos. The usual NFW halo rises with the cusp towards the center, 1 over r, as I said. And at least for dwarf spheroidal galaxies, where certainly the halo is supposed to dominate, there is no kinematical evidence for a cusp. There is a chord distribution of mass there, so there is a problem, well-known problem. Let's see what we, and because of this problem, when one fits with the halo models, the rotation curves of galaxies, it's a parameterized halo model, which is not like the NFW. It has a core, and it has usually 3 parameters: dispersion of velocities of the dark matter particles, the radius of the core, and the mass-to-light ratio of the disk. Usually it's 3-parameter model which you use to fit rotation curves that you see in nature. Now, Mond arose from a perception that the phenomenology that is connected with dark matter does not have a natural length scale, does not have a natural mass scale, it has a natural acceleration scale. And one can easily see this in the data. Again, for those galaxies in the Ursa Major group, we have plotted here in a log-log plot the dynamical mass-to-light ratio, mass measured by virial theorem and so on, against the size of the galaxy up to the last point of the rotation curve. And in this plot, first of all, you see that there is a mass problem because the mass-to-light ratio is about 10. It should be about, for stars, should be of the order of unity. So there is a mass deficiency, a mass problem. But there is no big correlation between the points. There is no order in this matter. If you replot these same points against acceleration at the edge of where the rotation curve ends, centripetal acceleration, you do see a correlation. The higher the acceleration, the lower the mass discrepancy. And the mass discrepancy really disappears for an acceleration of the order of 10 to the minus 8 CGS. Okay? That's the scale of the Mond paradigm, of course. And even before I begin to summarize what the Mond paradigm should be, one should ask what the physics could be behind such a strange departure from ordinary Newtonian physics. And there are several possibilities. It could be a modification of the notion of inertia that we have. It could be a modification of Newtonian gravitation. It could be something else. we have as an example the dipolar dark matter model of Luc Blanchet. We heard a little bit in the talk yesterday about this from him. In the first case, what you do is, of course, the Mond formula says that you have to change this Newtonian law to this form, and the interpretation in this would be that mu measures reduced inertia as a function of accelerations. It's not a fixed inertia for particles, but depends on the acceleration. Now, there were attempts to make a theory out of this idea by Milgrom in the 90s. It requires non-local physics, which means if you want to write an action for the theory, the action is not the integral of a local Lagrangian. It's a complicated kind of physics that is usually not seen in theoretical physics. It's very hard to work with. There are very few results that have been gotten out of this. So in fact, we know very little about this kind of possible physics. On the other hand, if you go for the modification of Newtonian gravitation, you take that law, you solve for the acceleration, and you interpret the right-hand side as a force in a modified gravity theory. So acceleration is still force per unit mass, but it's a modified gravity theory, not Newton's. So it's a new force, a new gravitational force. And I would like to show you that this idea, the second form, can be made into a reasonable non-relativistic gravitational theory. I will start with Newtonian theory to introduce the concepts. The acceleration is minus the gradient of the gravitational potential. Here in France, you usually say plus gravitational potential. I come from a country where we put a minus. There's a difference in sign. And the Lagrangian for the phi potential would be that one. It's the simplest rotational invariant Lagrangian, which has a coupling to the density of matter. And the coefficients you put in because you know what you want to get out of it. If you introduce the Euler-Lagrange equations, you will get this equation as an equation, field equation. That's the Poisson equation, which you know to be equivalent to Newton's 1 over r squared universal gravitation law. So this is Newtonian theory in Lagrangian form. And now this is the part which it's easy to modify. That's the only place where you can tamper with a theory like this. And let's see how you do it. You write the Lagrangian in this form. Just replace this by a function of it. And because this has dimensions, you have to introduce a scale of acceleration in a natural way. And to get the units right, the Lagrangian must look like this. F could be, of course, any alt function. That's what you, now let's see what equations result from it. That's the field equation, a modified Poisson equation, where the mu function, which I will talk a lot about, is just the derivative, related to the derivative of this f function. And if you compare with the Poisson equation for Newtonian gravity, and you remember that the divergence of a curl is always 0, then you get the first integral of our new equation to be this, where H is some computable vector field. The divergence of this will give you back this equation. Okay? That's the first integral. In spherically symmetric situations, this will just go away by symmetry. And even for a disk galaxy, numerical work shows that it's a small correction, 10, 15%. So suppose we ignore it to start with, then you replace the gradient of phi by minus a, you get this equation, which is the Mond equation. So the Mond equation is some approximate solution to this theory of gravity, modified theory of gravity. Of course, now we have to take A0 to be Milgrom's scale that I mentioned about, which is this number here. And about the mu function, the appropriate shape of the mu function is something like this from empirical considerations. It goes to 1 at large argument, linear at small argument. In the one in the far regime, in the asymptotic regime, you get back Newtonian physics because mu is 1. And in the linear regime, you are in what is called the deep Mond limit or deep Mond regime, which has rather peculiar relations, which I will use later on. So this is a summary of modified gravity a la Mond. Okay, now the Mond equation, which is written here, has some important deficiency. I said it's an approximate solution to the full theory of gravity, but if you use it all by itself, you could get into trouble. For example, suppose you have two masses which are attracting each other. You write the Mond equation for both of them, and then you multiply the upper one by m1 and the lower one by m2, m being the mass of the particle. You get this combination, and this is definitely not equal to the rate of change of the momentum of the system. In other words, momentum is not conserved in this, with this simple law. Another example of problems that could occur, you take a nice galaxy, some star orbiting the galaxy in the plane in circular orbit, and you look inside the star at an element of fluid. This element of fluid always exposed to extremely large accelerations on the A0 scale, factors of 10 to the 8, 10 to the 10 easily. So it must have a mu very close to unity by Mond itself. And the other elements nearby, same story. So the center of mass of this collection of fluid elements should be moving with mu equal to 1 in a Newtonian fashion in the enveloping or environmental field. And yet we know that the star is supposed to be moving according to a Mond law, which is very different from the Newtonian one. So you get a contradiction, which I call the part-whole paradox. You get two different results according to the viewpoint, small scale physics or large scale physics, which is of course a result of the fact that the Mond equation by itself does not obey conservation of momentum in general. The full theory does, but this is an approximate result. So watch it when you use this formula. It can be used with caution, and sometimes you get easily many interesting results. For example, Tolley-Fisher relation can be explained with very little work. This would be the Mond equation in the limit of small acceleration, when mu is a linear function of the argument. Suppose that in a flat galaxy with circular orbits, we write the centrifugal acceleration in this form. And for the gravitational field, I just write the Newtonian form. That's what the Mond equation is telling me. And I use just imagine that all the mass is concentrated in the central part of the galaxies, and I'm moving in the periphery of the galaxy. You can see that the Mond equation is obeyed in terms of both sides are 1 over r squared. And from the coefficients, you get this connection, which looks like the Tolley-Fisher law, mass versus proportional to the fourth power of the velocity. It's that line which is plotted here. It's parameter free. There is nothing to adjust. And this is data from gas-rich spirals where you don't have the problem of figuring out what the m over L ratio of the stars are, because the stars count for very little in these small gas-rich spirals. And so, and you can see that the fit is very nice, and there are no parameters being adjusted here. It just falls in completely. If you go by lambda this CDM in a naive way, you imagine that the baryons in the galaxy make up a definite fraction of the virial mass of the system. You will get a prediction like this for the relation between m and v, which has a slope of 3. And it looks wrong in slope and in normalization. And yesterday we heard from Gary that it's very hard, really, to reproduce this line by these concepts, even if you introduce all kinds of complications. So, in fact, with Mond, it's very easy to obtain this particular fact. You can also get the nice fit with all spirals, mixed gas-rich and the other ones. You will also get a nice fit for the Tolley-Fisher law. So this is one success. You can also understand the shape of the rotation curves. This panel shows 15 rotation curves from the Ursa Major group. In each galaxy, I'm showing where the gas will give you a Newtonian rotation curve like this, and the stars like the dotted line here. And the black line would be the result of applying the Mond formula with this data. And in this case, this following mu is used, which is called the simple mu. I will use it repeatedly today. So the predictions for the rotation curves are using the Mond formula. And you can see that it's very well fit. The only fitting parameter is the mass to light ratio of the disks. Now, regarding the numbers that you need to obtain these nice fits, and in fact, I should say that, even before I go on, I should say that yesterday we heard a talk by Francois Combe, enumerated something like a dozen tests of the Mond idea, empirical tests, in which in many of them Mond is actually quite better, does a better job than the dark matter idea. So that what I'm going to do is just limit all the discussion to just one of these tests, really. The M over L ratios, which we get from the previous procedures, are plotted here against the color index of the galaxy, both for blue magnitudes and for the infrared magnitudes of the galaxies. And the dark lines come from population synthesis models which were made after the particular measurements which I mentioned, particular Mond fits actually. And you can see that the fit is quite good, particularly in infrared. Okay, so you could say that if you believe population synthesis models, then Mond can explain the shape of rotation curves and the normalization without any fitting parameters, parameter-free theory, right? You put in physics and you get out predictions which work. Also, the fact that the infrared M over L comes out almost horizontal means that the infrared form of the Tolley-Fisher law is also a consequence of Mond, not just the baryonic form, but the older infrared form is also a consequence. Now, you can also compare dark matter halo fits with what I showed you before. There are 4 dark matter halos compared with the rotation curve of a particular galaxy, which is this one here. I'm just showing one of a set of fits that have been made by this group. In this particular, you can see the contributed Newtonian rotation curves for gas stars and for the assumed halo. Okay, this one, of course, is a model that doesn't use an halo, just shifts the H1 contribution, and the dark curve is the prediction, and the better model is always the Burkert model. Here you can see the residuals, okay? And let's compare this with Mond. So I will just just replace one panel. This is a Mond fit of the same galaxy using the standard Mond formula, which I said is approximate, and the simple mu function. And you can see that the fit is about the same quality as the Burkert model. Remember that this has only one fitting parameter and this has 3. So we have gained in simplicity of model construction pretty much with the same accuracy. This is very typical of the things you see with Mond. So Mond is successful in describing galaxies. But Mond doesn't do away with the need for dark matter. We have a problem with clusters, and it was noticed by Milgrom early 1980s that Mond, you really have to supplement with dark matter to understand the dynamics of clusters of galaxies, and so he postulated that galaxy clusters must contain a lot of gas that we still don't see. Okay? Now, just a few years later, the X-ray emitting gas in clusters was discovered because of new satellites, and in fact, it did add a factor of 5 in the mass of clusters, baryonic mass, but that wasn't really enough to do the job, and you can see it in the newer data. This is a plot of the dynamical mass of cluster versus the observed mass in baryonic gas, basically. These are the data, and this is, of course, if there were agreement between the two masses, and there's a factor of maybe 5, 6, even more, which has to be filled in by dark matter. There is a discrepancy. This is the mass, dark mass, the missing mass discrepancy. If you use, excuse me, if you use Mond virial theorem instead of the Newtonian one, you get this kind of a dynamical masses. You can see first few things. First of all, it's broader than this distribution. The reason is that the estimator of mass in Mond is a V4 estimator, not a V² estimator. So all errors get fattened up. But even then, you can see that the clusters are closer to the diagonal than in the ordinary, than in the dark matter fit, or the ordinary, understanding. But the distribution is above the diagonal, really. So there is still a need for dark matter, a factor between 2 and 3. So there is a problem, remaining problem with clusters. And the question is, what do you do about this? And by the way, the lensing, gravitational lensing, affirms this conclusion. In gravitational lensing, that example, famous example, you use the geometry of this usual diagram to determine the bending angle of the light theta. And from that, in general relativity, you can estimate the mass of the lens. Okay? It turns out that lenses have masses which are anomalously large, meaning that there is more mass than you see there. I mean, anomalously large compared to the baryonic mass that you see in the cluster. And so this, and in fact, the masses that you get are comparable to what you deduce from the dynamics of the galaxies in the cluster. So in fact, you get a picture consistent with dark matter. And bullet cluster is another famous example which seems to tell you that there is dark matter in the clusters. And here you see a collision of two clusters at about 4,000 kilometers per second. Collision expelled all the X-ray emitting gas, which is red in this fake color picture. When you look at the lensing map for the clusters, you see that the isophotes are centered on the galaxies. Okay, so it is as if the mass is here, whereas this picture shows you that the gas is somewhere else. And the gas is most of the baryonic mass that you see. So this is telling you basically that there is more mass in some form that you don't see near the galaxies than in the gas, which as most of the baryonic mass. It seems to be a very good support of the dark matter hypothesis. I will bring this up later on. So this is another affirmation that really Mond has a problem. The new thing here is the delocalization of the dark matter and the baryonic matter, right? They're in different places. This is the first example which was discovered of this delocalization. And I will come back to this problem for Mond. But we have a problem of Mond. And how do you fix it? There are some suggestions. Milgram, for example, holds to the idea that there is still baryonic matter in clusters which has not been discovered in some form. For example, little clouds which manage to not to be disrupted over Hubble time. And what it needs is mass which will provide a contribution 0.025 to omega on a global scale, on a cosmological scale. That's the need that you need. Of course, from the point of view of primordial nucleosynthesis, you are allowed about 0.04 omega of 0.04 in baryons, and only less than half of it is really known in all forms. So there is place for this amount of baryonic matter in clusters. You wouldn't contradict anything. It's just not seen. Sanders had the idea that massive neutrinos are making up for this missing dark mass that you need. And what you need is three classes of neutrinos, three kinds of neutrinos, with 1.9 electron volt of mass for each kind. This is consistent with the tritium-Roshan experiment on the bound on the mass of the E neutrino. It's consistent with the oscillation, neutrino oscillation experiments. It's not consistent with implications from cosmological models, but then the cosmological models are done always with general relativity, and we're casting doubt on that. So perhaps this will work. And also lately, elementary particle experiments in Fermilab seems to be easier to interpret them if there are one or two kinds of sterile neutrinos in nature with masses of the order of an electron volt. Sterile neutrinos, they have only gravitational interaction, not weak interaction. Now, if you have a couple of species with 1 electron volt, those might be the neutrinos that Sanders needs. And there is a third way of solving the problem of Mond, which is to say Mond is actually written down as it's incomplete. The description that I gave is incomplete. And the reasons for thinking of this are the following. When you look at clusters, you could actually remove the problem of clusters if you use A0 factor of about 2, 3 larger than the one that you use for galaxies. It looked kind of stupid to do this, but if you do it, it actually removes the problem in clusters. Now, if I have time to discuss the cosmological microwave background from the point of view of Mond later on, I will mention that bigger A0 in cosmology lets you fit things much better than using the original A0. It seems like A0 grows with scale, mass scale or length scale, and you can actually put this idea into a decent theory in the following way. The AQUAL theory, which I mentioned, the non-quadratic Lagrangian theory, can be changed a little bit in the direction that we need. I call it scale-dependent critical acceleration. Instead of this AQUAL Lagrangian, take this one. The red factors are new. Exponential of the gravitational potential divided by the square of a scale of velocity. S is a velocity, scale of velocity. What this is doing is the following. You're dividing A0 by this exponential. Phi is negative in a gravitational system. The deeper the gravitational potential, the bigger the factor, or the smaller the factor e to the 2 phi, and therefore the effective A0, which plays a role in the theory, is actually bigger than the nominal A0. And in fact, if you would take S to be about 1,000 kilometers per second in a cluster where the velocities are of order 1,000 kilometers per second, rich cluster, the factor e to the minus phi over S squared is of the order of 3. That's exactly the factor you need to fix the problem with the clusters. If you go for a galaxy where the velocities are 200 kilometers per second, the factor e to the minus phi over S squared is 1.04 or something like this. So it's really essentially 1. All galaxies have the same A0, the original A0 more or less, and you're fine. You have removed the problem in a very simple way. This is the equation that comes out of that Lagrangian, and it's different from the AQUAL equation in a very important, it's not only more complicated, it's actually a different class of equations. The Newton's iron sphere theorem doesn't work here. What is the theorem? If you have a spherically symmetric system and you measure the gravitational field on a sphere around the mass, you can deduce the mass uniquely. This doesn't work in this kind of theory. It works in AQUAL, but it doesn't work in this theory because of these extra terms. And no matter how you massage the equation, you cannot bring it to the form of the AQUAL equation. So there is no iron sphere theorem, which means part of the mass which is producing a gravitational field could be outside the general region of the where you integrate the gravitational field. There could be sources outside which are being counted in the gravitational field, something which goes against our Newtonian intuition. This would be automatic in this kind of theory, and of course it could even help us with the problem of the bullet cluster, because in the bullet cluster the problem is that there is gravitational field. We don't seem to see the sources of it inside the region of the gravitational field. The sources seem to be outside, but that might be okay with this kind of a theory. I will return to this issue in a moment, but I should tell you that I'm actually getting ahead of myself, because we really, to understand the lensing problem, you really need relativistic Mond, because light is a relativistic phenomenon. You cannot really fake all these things with non-relativistic physics. So how do you go about producing relativistic Mond? And what could you do with such a theory? You could also handle, for example, how to describe pulsars in black holes. You need relativistic Mond if you want to do it a la Mond. How to construct cosmology a la Mond, and how to describe gravitational radiation in a Mond universe. You need all this relativistic Mond theory to deal with a number of questions. And the question is, how do you do all this? So let me go on to describe how you construct a relativistic version of Mond. There was a first try many years ago, which has an interesting idea, which I must explain. I will always take C equal to 1 in all the description of relativity. You replace the potential of the gravity by a scalar field for reasons of relativity. And then you write down the equation for phi as a covariant form of the AQUAL equation. T is the trace of the energy momentum tensor in relativity, comes in place of minus rho, the density of mass. Okay, so that's a relativistic form of the AQUAL equation, no change really. G is the metric, and you have the A0 of Milgrom built in. You use this phi field that comes from this equation as a conformal factor that multiplies the metric that you start with, which of course comes from the Einstein equations, and you interpret the new metric to be the metric where matter moves, the metric where everything happens, you know, where we and I and you exist. Now, in such a theory, the gravitational field that is derived from the true metric is the Newtonian potential plus phi to a good approximation. Phi as here units of the gravitational potential in this particular way of setting things up. So this actually plays the role of the dark matter, right? There is some addition to the gravitational potential. Okay. Now, in this theory, unfortunately, you do not get an anomalously large light deflection that you need to understand the lensing phenomena. The reason is that it's known, and this was, for example, reminded to us by Gilles Esposito Fares yesterday in the little symposium. In a conformally coupled metric like this, there is no change in the lensing pattern. It's all the same as in the original metric. So conformal factors cannot give you anomalously large light deflection. And in this theory, the perturbations of the scalar field propagate faster than light, which might scare you. Gilles mentioned correctly, I think, that this doesn't have to worry you. There's some complexity in the notions there which allows you an escape. And it certainly doesn't contradict any facts. But the first problem does. It's against the observations. So this theory falls down. The simple AQUAL, relativistic AQUAL falls down. And you need to improve it. A breakthrough was achieved by Sanders, who said the following. Suppose this is the metric of spacetime. Suppose you have a vector field, constant vector field, of unit size in the universe for some reason. Imagine the space perpendicular to the direction of this 4 vector to be squeezed by some factor, and along the vector to be stretched by the same factor. Okay, basically you obtain a space-time which has this line element. Okay, you can see here the space perpendicular to the vector being squeezed, and you can see the space along the vector being expanded, okay, by the same factor. And the whole metric which has appeared here, G twiddle, which I will always call G twiddle, is the metric where matter is supposed to move. So the theory is really how to construct the physical metric of matter. For the phi field that you need, you will use the AQUAL equation as was. And the vector field is just a constant vector field all over space-time. The only problem with such a, by the way, the bending of light will come out okay in this theory. This was the reason for doing this. But the problem is that a constant vector field all over space is a non-covariant notion, because if you change coordinates, you change the components of the vector, and it's no longer constant. So it's not a covariant theory. We don't like these things today. So there's something wrong. And you can solve this problem by rearranging these ideas. And what comes out is really the Teves theory, tensor vector scalar theory. And this is the idea. You start with the usual gravitational action of Einstein, no change. For matter, you use the usual action of matter that people write for whatever fields FA that you have. But whenever you need the metric in this Lagrangian, you use the G twiddle metric, which I introduced in the previous transparency. So there is a vector field in the theory. Now, this vector field is given a dynamics. It has a Lagrangian of its own. It's not a constant. It has to be calculated. This is the Lagrangian that is being used. Now, it has 2 coupling constants, which are these 2 Ks. Now, in the original version of Teves, only this term appeared. It was yesterday, Gilles reminded us that the theory with only this piece of the Lagrangian as on physical feature. It's unstable. This was discovered by Contaldi, Weissman, and Withers, 2006 or something like this. And you really have to add other quadratic terms in gradients of u of the vector field in order to make this, resolve this unphysical problem. Today, we add this extra term. So this is the improved Teves, you could say. The vector has to be a unit vector, and this is a Lagrange constraint to force the vector u to have unit length and to be time-like. That's what we really need. And finally, you need an action for the scalar field. In this action, there is a new function f, which parallels the f function in the AQUAL theory. And there are two coupling constants, little k and a scale of length, L, scale of length, which is big scale of length. This piece of the Lagrangian, which is a bit unorthodox, is put in there to eliminate the superluminal propagation of scalar perturbations. If you don't like it, you can actually get rid of it. So this is the basis for Teves theory. I won't calculate the equations. This is not for a colloquium. I will tell you, however, what is in Teves, what consequences. Teves has a GR limit when all these k's vanish and the L becomes large compared to the scales of your problem. So you can get back the GR, which is well tested in many respects. You can actually rewrite the theory in one metric, not two metrics, one metric. And without a scalar field, then the vector Lagrangian becomes a big mess. This theory is good for actually understanding conceptual things, but it's not very good for calculating models. It's just too complicated, but there is such a possibility. The Teves theory will reproduce AQUAL non-relativistically. That is, the non-relativistic AQUAL that I showed at the beginning will come out, at least we know this for sure, in quasi-relativistic situations. The A0 of Milgrom gets constructed out of k, little k, and the L scale. Remember, C is equal to 1. This theory has a Newtonian limit at strong gravitational fields, so you return to normal life. And there is, of course, a post-Newtonian regime and governed by 10 post-Newtonian coefficients, the PPN coefficients. In general relativity, they have standard values. 8 of them agree with general relativity exactly in this theory. 2 do not, what's called the 2 preferred frame coefficients, called alpha 1 and alpha 2 in Will's Bible of the PPN formalism. Those coefficients are not 0 like in GR, but one can tweak the coefficient, the parameters of this theory to actually make them agree with the bounds that have been set on these two parameters. This was done by a student of mine, Sagi. And so the theory looks, as a starting point, looks usable, we could say. Okay, there have been other relativistic Mond theories produced over the years since then. I can mention yesterday Einstein-Ether, Mond-Einstein-Ether theory was mentioned, and there are others. All of them have some feature that came from Teves. There are some imitations of Teves. And in the last 5 years, maybe, there has been a strong effort to test Teves against gravitational lensing and against cosmology. And I want to discuss that as far as I have time. Question is, how much time do I have? About 15 minutes, 16 minutes. Let's make a try, okay? Now, you remember this lensing, famous lensing diagram with Einstein observing, since he was the first to predict there is such a thing as lensing. And usually the metric that you use in GR to analyze the results of lensing has this form with one gravitational potential in two rolls. This is the Newtonian gravitational potential. This is the method you use to calculate lensing. Okay? Now, in Teves, you use the same metric. The same metric is used, except that phi has this meaning that I've already mentioned before. There is a contribution from the scalar field. And phi is calculated by a special equation which uses the baryonic mass density as its source. So there is no dark matter in the whole business. It's all baryonic. These people actually analyzed originally the lensing in Teves in some theoretical detail. and they used always a point mass lens approximation for the galaxies that do the lensing. This was directed more or less at galaxies, not at anything else. Let's see what's okay. They found, for example, that if you go to the deep Mond regime, I should mention one very important thing before I go on. I forgot it. In respect to this statement here, suppose you have a system where Mond describes the dynamic correctly, galaxy or something. This you can easily show from this formula that the Teves will give you gravitational lensing for this galaxy, which agrees with the prediction from GR with the amount of dark matter necessary to describe the dynamics. In other words, you can get an agreement between GR plus dark matter and Teves for systems where Mond works in the dynamics. How do you tell the two theories apart? You go to the very far asymptotic limit where the phi part of the potential is already different from the contribution to phi n of dark matter. And there you try to see what's the difference. And this refers to this statement here. In the deep Mond regime, these people find that the bending of light, the bending angle of light is uniform regardless of the parameter, impact parameter of the light ray. You always get the same bending angle as you would get in GR if you had an isothermal sphere distribution of mass. There is no dark matter here, so this is a point particle here. You get the same effect in Teves. Now, if you have two-image lensing, in other words, strong lensing, the difference in magnifications of the two images is more than 1 in this theory. In GR, it's 1. So there is a difference which can be tested for. And if you see a difference in the time arrival, in the arrival time of signals in the two images produced by a lens, you can actually use that to compute the mass of the lens, and it's information which is independent of the one obtained from the amplifications or the positions of the images. So there is a way to check the internal consistency of the predictions of the theory. Of course, this is a very theoretical approach. More phenomenological was an approach by this group. They looked at a group, 17 clusters which are lensed into two images from a catalog called Castles. They modeled the galaxies which are doing this, which are usually ellipticals. They modeled them as both Ehrenquist spheres or point lenses. And they obtained the conclusion that when you calculate the mass of the lens from the image positions or from the amplifications, you get comparable masses. That is, there is an internal consistency of the predictions. And also the masses come out reasonable for the baryonic mass of the galaxy. The M over L comes out of the order unity, which is what you would like for a baryonic galaxy. There is no need for dark matter, so there is a consistency with the idea of Mond, and that's what is said in this problem. There is another analysis made by these people, which is quite similar in conclusions. They actually took into account already departures from spherical symmetry, and for 10 doubly imaged quasars from the same catalog, and even one quadruply imaged quasar, they actually obtain masses by the two methods which are comparable and are reasonable. In other words, the same kind of results as before. There were outliers. There are galaxies which make problems. There are lenses which do make problems. So it couldn't be that you still need dark matter at the level of galaxies from this evidence. And there's, in fact, conflicting opinions on this. For example, this group have two papers claiming that you need to add dark matter to understand lensing in galaxies. I'm talking about the level of galaxies, which was always explained. Galaxies were always treated well by Mond. They claimed that for lensing, you need to introduce dark matter. And the reason was that they found a conflict between their Teves mass estimates for 18 lenses in that catalog with the masses that come from luminosities and a suitable M over L ratio. But there is a reanalysis of this same sample, very recent one. They looked at 10 lenses, those 10 lenses in this group, which can be treated as spherical. They found that if you use Teves with my toy F, the F which I used in the original paper was kind of a just a made-up f to do the calculations, not particularly, it's a toy f, or you can use an f which will give you the simple mu, which is so empirically successful. In both cases, they find out that you don't need dark matter. You can actually understand, get a good M mass for the galaxy, which looks like the mass of the baryonic mass, without adding any dark matter. Why is there a contradiction between these two approaches? Apparently, the first group used luminosities for the galaxies, which were determined through fixed apertures. And that leaves out a piece of the mass, different amounts of mass in different galaxies, so it actually makes some complication that need not be there. So it's possible, quite possible that galaxies are completely consistent in their lensing with Teves. Is separations of images, okay? Now, you know that this has been a problem for dark matter, the dark matter approach. What I mean is the following. This plot is a plot for this merged two catalogs of lensing. And I'm looking at the squiggly line, dark line. This is the data. The separation of the two images of a quasar versus, not the separation, this is the separation, and this is the frequency with which you find quasars separated by such an amount. So this is the probability, really. So this is empirical, and these are models. The three solid lines are Teves, three different mu's, and the two dotted lines are GR without dark matter. In both cases, you take a cosmology, an open cosmology with lambda equal to 0.5, baryonic 0.04, and no dark matter. You model the galaxies as Ehrenquist spheres, and you take the distribution of masses of galaxies from the Fontana mass function, and you get those predictions. And the dashed dotted, or the heavily dashed line, that's LCDM cosmology, modeling the galaxies as isothermal spheres of dark matter. And again, you use the Fontana mass function to get the mass distribution. And those are the predictions for frequencies of separation of quasars. And I think that of all the models, the Teves models are actually doing maybe not very well, but not very bad, right? They are actually the better ones. Of course, this is a small sample, but it shows that there is a potential from large surveys of lensing to actually check these theories very well. So let me go on. To spherical clusters, we had a problem in clusters from dynamics. Let's look at your work of this group here. They looked at three clusters, big, rich clusters, and they used Teves to calculate the lensing pattern, the shear and the convergence of the lensing map. For this, they used a mass profile, which was a synthetic mass profile taken from a sample of clusters from the SDSS survey. So the actual mass distribution is some unified model. For this particular cluster, you can see the distribution of gas and mass of gas and galaxies that are being used. And they found that they have to put in a dark halo, which is marked here. This is for the mass distribution. This is the Newtonian gravitational field that comes from the galaxies and from the including the dark matter, actually, including the dark matter. And these are the predictions for the renormalized, or actually, we should say normalized shear and convergence if you use only gas and galaxies a la Mond, or if you include the dark halo. You can actually fit the observations with a dark halo, which contains a mass quite comparable to the mass in galaxies and gas. What is this mass? They go for neutrinos. It could be anything, really. And so you still need dark matter in clusters, just as we found out from the dynamics. So the lensing is telling you this. There are other groups that confirm this problem. And let's go back to the bullet cluster. These people actually made a Teves model of the lensing of the bullet cluster. They also have to add dark matter in the form of neutrinos, as they say. But you can actually make models. The question is whether you believe that there are so many neutrinos and they are in clusters. This is confirmed by this other group. You need dark matter to understand the lensing pattern. And in fact, this other group has a stronger word, and they say it's impossible for Teves, the AQUAL equation in Teves, to give you the separation of the baryonic mass and the lensing center that you see in nature. The equation just won't give you that. That was their conclusion. But there was a recent review in Science by Ferreira and Starkman that noted that in Teves there is no Birkhoff theorem, there is no analog of the iron sphere theorem of Newton, so you can actually have matter here being the source of the gravitational field inside. Okay? In other words, it's just what you need to try to understand a situation like this. The mass can be outside the general region in which you measure the gravitational field, and therefore without specific calculations you really don't know. You have to you cannot go by the iron sphere theorem to obtain conclusions. Now, I think I've said enough about lensing. Let me try to do something about cosmology if I have a few minutes. There are some trivial aspects of cosmology. For example, Robertson-Walker models work. You can calculate luminosity distances, angular distances, just like you do in GR. It's very similar. There was an important paper by these people, Ferreira, Bourliot, Motta, and Scordis, that showed that you can obtain constraints on the mu function of the Teves. That comes as a derivative of the f as in AQUAL. You can obtain constraints just from isotropic cosmology. Not every mu will work. So you know something about. Yesterday from Gilles, we heard that there is a way to constrain mu from solar system measurements. So one can actually say something about this function mu. Now, you remember that in scalar tensor theories, which have a scalar, there is a tendency for G to be a time-dependent function, right? A time-dependent number. A student of mine, Sagi, and myself actually checked that G is completely constant in Teves. Despite the fact that there is a scalar field, G is a gravitational constant. However, the A0 of Milgrom actually obtains a slow decrease in time in expanding cosmology. Unfortunately, it's not a very strong effect. And when you look at galaxies, a big redshift of 2 or something like this, we don't know enough about the rotation curves there to actually check whether this is true. It will be possible in 5 years, but not just now. Okay, now let me, of course, the great challenge is to have Teves duplicate the success of lambda CDM for fitting the power spectrum of the cosmological microwave background, right? That's the real challenge. Let's see how Teves does. The theory of fluctuations, cosmological fluctuations in Teves was developed by Scordis in one big paper from ab initio, from the beginning, and this was used by these people to make the following fit of the cosmological power spectrum of the background, data available in 2006. You can see here the dotted line is general relativity, the usual lambda CDM model. The solid line is Teves, where you put in omega of 0.17 in neutrinos, in sterile neutrinos. Okay, you need to have some dark matter at the cosmological level, but you get a fairly good fit on those points which were known in 2006. I'm told by Pedro Ferreira that you can actually fit the further peaks which have been shown to exist, but just continue pushing these models harder. If you don't have the neutrinos, the Teves just fails completely. So you still need some kind of dark matter in the theory. Now, because, and by the way, there is an affirmation of this conclusion from these people here, you do need neutrinos, but you can actually fit, not bad, the cosmological power spectrum. Since the theory seems to be degenerate, Teves and GR, from this point of view, you need some other way to separate. I guess that's the end of the hour, or? By coincidence, yes. Just a couple of minutes to tell you the punchline, okay, and then I'll summarize. There is a statistic that will tell Tevez from GR using this data, and this comes from this paper by Jean Ligore, Bain, and Dodelson. The idea is the following. This is the metric for a perturbed Robertson-Walker model. There are the two famous potentials, psi and phi, which are the ratio of each of these potentials to the mass over densities is a number which varies with theory. So if you could measure this number, you could distinguish between the two theories. The problem is that mass over density is something hard to measure because you always have questions of biasing. So you can invent basically any biasing scheme and get different results. These people actually showed how to get around this thing, and it's just what I said. And what you do is the following 6 easy steps. You make from a galaxy survey an autocorrelation function of the galaxy number over density versus the divergence of the velocity field of the galaxies. This can be done and has been done. Okay. Now you remember that mass conservation gives you this relation between the divergence of velocity and the mass over density. Involved here is the law of growth, the growth factor, how it evolves in the cosmology, the growth factor big D. So using this equation, you now have an autocorrelation of galaxy number density with mass over density. Okay? Now suppose or remember that lensing is a measure of the Laplacian of the difference of these two potentials. Okay? Then what you do is use a lensing survey in a to make a cross correlation of the shear within the galaxy number over density. Okay, that's from a different survey. You do this different correlation function, compare it with this one, kind of divide one by the other, and in a figurative way you have determined the ratio that you need to distinguish between theories. These numbers should be different in Tevez and GR. Now, actually what you do is, what these people do, is they invent a statistic whose mean over various subsamples will give you the ratio you need. And this statistics is being now tested. What are the expectations? Here are predictions for, by the way, this e.g. this statistic in general relativity is predicted to be independent of scale, but varying with redshift. So you have 4 panels for different redshift bins. The predictions of general relativity are horizontal lines. You have predictions in red for the Gabadadze, Dvali, Porati model, modified gravity. I guess I got the order of the people wrong. There is a prediction for f of r modified gravity, and there are Tevez predictions for 3 different mu functions. Okay. Now, what are these error bars? They're not error bars. They're estimates of the precision which will be available in measuring this EG from various surveys which are listed here, starting from LAMOS, which is an optical survey, 1 million galaxies. The data is already in, but it has not been used. Going to the square kilometer array survey in radio, billion galaxies, and the synoptic telescope survey, optical, also 1 billion galaxies. Those should give you the smaller error bars that you see here. And it's easy to see that you will be able to tell the theories apart by this statistic, even if you cannot by checking the power spectrum. Now, in fact, last year I was in Princeton, and a group in Princeton put out a paper saying that the problem has been resolved against Tevez. And the title was Confirmation of General Relativity on Large Scales from Weak Lensing and Galaxy Velocities. They took a sample from the Sloan Digital Survey, a sample of 70,000 ultra-luminous red galaxies, the biggest sample they could get, and they used it to obtain the following diagram. Let's see, why is this not working? And they claim on the basis of this that Tevez is ruled out, although f of r not quite ruled out. In my defense, I should say the following. There are 3 points which should be taken into account. First of all, the error bars are really big. And you need a survey of order of 1 billion galaxies to really get the error bars to be small, negligible, you could say. That's one thing. Second thing, that what was the second point that I wanted to, yeah, this point was actually calculated by the Zhang paper to be the value in some scale for a sample with redshift between 0.4 and 0.6. Nobody has calculated what happens at this low redshift. This is considered a low redshift in this problem. So in fact, this number is a fake. And third, this number is obtained from a Teves theory, which has only the first piece of the Lagrangian, the vector Lagrangian, the Maxwellian type Lagrangian. And we heard, for example, from Gilles yesterday at this Mond symposium that this one term Lagrangian for the vector field leads to an unphysical Teves. There is an instability in the theory. One could also mention that the ppn coefficients that were problematic in Teves cannot be pushed under the bounds set by experiment with this kind of a Lagrangian. You really need the second term in the Lagrangian, and that means calculating anew the prediction here. So this prediction is actually relevant to the question at hand. You actually need to use a physical theory to do this. Okay, so I'm summarizing, which is just 1 minute. We have seen that Mond unifies disparate facts about dynamics of galaxies at all scales, but has trouble with clusters. A lot of the things I haven't said, they were well summarized by Francois Comte yesterday in this discussion that we had, the Mond symposium. Mond can be implemented as a non-relativistic modified gravity called AQUAL, the first theory which I discussed here. It is possible that Mond is just too conservative, that you need to allow for the A0 to be a running coupling constant. And I showed you how you might go about constructing a theory like this, non-relativistic at least. Mond can be implemented as a relativistic theory. There is Teves, and there are variants of these theories which are being tested today. Teves works well for lensing with galaxies, and it actually can supplant dark matter in cosmology as far as we can know, as far as we know at the moment. But it does less well for clusters because you always need some kind of dark matter in clusters. The question is whether this running coupling constant will help you in this respect. And that's about all that I wanted to say. Thank you.